somewhere in the flat, sun-scorched plains of southern Texas, a rocket stands on a launch pad. It is the tallest, most powerful machine ever built by human hands, taller than the Statue of Liberty, heavier than a fully loaded cargo ship, and inside that rocket, strapped into their seats, hearts pounding, palms sweating, are 6 human beings. 6 ordinary people who made the most extraordinary decision any human being has ever made. They volunteered to leave Earth. Not for a week. Not for a month. Not even for a year. They volunteered to travel to Mars, a planet so far away that by the time they arrive, the Earth will be nothing more than a pale blue dot in the sky, barely visible to the naked eye. The whole world is watching. Billions of people glued to their screens, children pressing their faces against classroom televisions, families gathered in living rooms, scientists in mission control rooms biting their nails, politicians giving speeches about the triumph of human ambition. It is, without question, the most watched event in the history of civilization. The countdown begins. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 ignition. The engines roar to life with a sound that shakes the ground for miles. A pillar of fire erupts beneath the rocket, and slowly, impossibly slowly, the massive vehicle begins to rise, faster and faster. The cheering is deafening. People are crying. Strangers are hugging. It is a moment of pure, unfiltered human triumph. We did it. We are going to Mars. But here is the thing nobody is talking about. Here is the truth that gets buried beneath the celebration, the patriotic music, the inspirational speeches. Those 6 human beings, they are never coming back. Let me say that again, because I need you to truly understand what that means. They are never coming back. Not because they do not want to, not because they chose not to, but because the laws of physics, the limitations of our technology, the brutal reality of the Martian environment, and the fragile weakness of the human body have conspired to create a situation where returning from Mars is not just difficult, it is not just dangerous, it is, by every honest scientific assessment we have today, very likely impossible. And I know what you are thinking. You are thinking, wait, I have seen the SpaceX presentations. I have seen the animations of starships landing on Mars and taking off again. I have heard Elon Musk talk about a city of 1 million people on Mars. Surely we have this figured out, right? Surely the smartest engineers on the planet have a plan to bring these people home. And the answer is, yes, they have a plan. But a plan is not a solution. A plan is a hope dressed up in engineering jargon. And when you strip away the optimistic timelines, the glossy animations, and the billionaire confidence, what you find underneath is a problem so complex, so layered, so fundamentally terrifying that it keeps NASA scientists awake at night. It is a problem that involves orbital mechanics, rocket fuel chemistry, human biology, radiation physics, psychology, material science, atmospheric science, and about a dozen other fields of study, all of which have to work perfectly, simultaneously on an alien planet where the temperature can drop to negative 150 degrees Celsius, where the air is 95% carbon dioxide, where the soil is laced with chemicals that attack your thyroid gland, and where the nearest hospital is 225 million kilometers away. Today, in this video, we are going to go deep. And I mean truly, genuinely, uncompromisingly deep. We are going to explore every single reason why stepping foot on Mars might be a one-way ticket. We are going to talk about what happens to your bones after 7 months in zero gravity. We are going to talk about cosmic rays that can literally pass through the walls of your spacecraft and shatter your DNA like a bullet through glass. We are going to talk about dust storms that can engulf the entire planet for months, blocking out the sun and killing your power supply. We are going to talk about the psychological horror of watching Earth disappear from view, knowing that everyone you have ever loved, every place you have ever been, every memory you hold dear is on a planet you may never touch again. We are going to talk about the fuel problem, the landing problem, the gravity problem, the food problem, the water problem, the radiation problem, the medical problem, and the ethical problem. We are going to cover it all. Every angle, every detail, every terrifying, awe-inspiring, heartbreaking dimension of this question. Because this is not just a question about space travel. This is a question about what it means to be human, about how far we are willing to go, about what we are willing to sacrifice, and about whether the red planet that has fascinated us for thousands of years is a destination or a death sentence. So if you are the kind of person who is genuinely curious about the universe, if you are the kind of person who wants to understand the real science behind the headlines, if you are the kind of person who is not satisfied with surface-level explanations and wants to go all the way to the bottom of the rabbit hole, then you are in exactly the right place. Do me a favor, hit that subscribe button right now, turn on the notification bell, because what we are about to explore together over the next 90+ minutes is going to fundamentally change the way you think about Mars, about space exploration, and about the future of our species. Let us begin. Before we can understand why returning from Mars is so difficult, we first need to understand something that most people drastically underestimate, and that is the sheer, mind-bending, almost incomprehensible distance between Earth and Mars. We hear the numbers all the time. Mars is about 225 million kilometers from Earth on average. But what does that number actually mean? How do you wrap your head around 225 million kilometers? Let me try to put it in perspective for you. The Moon, our closest celestial neighbor, the farthest place any human being has ever traveled, is about 384,000 kilometers from Earth. When the Apollo astronauts went to the Moon, it took them about 3 days to get there. 3 days. That is a long weekend road trip, cosmically speaking. Now Mars, at its closest approach to Earth, is about 54.6 million kilometers away. That is 142 times farther than the Moon. And at its farthest, when Earth and Mars are on opposite sides of the Sun, the distance balloons to over 400 million kilometers, more than 1,000 times the distance to the Moon. So if going to the Moon is like walking to your neighbor's house at the end of the street, going to Mars is like driving from New York to Los Angeles, except there are no roads, no gas stations, no rest stops, no towns along the way. It is just empty, silent, radiation-filled void for 7 to 9 months straight. And here is where it gets really interesting and really terrifying. You cannot just point your rocket at Mars and fly there in a straight line. That is not how orbital mechanics works. Earth and Mars are both orbiting the Sun, but at different speeds and different distances. Earth orbits the Sun at about 108,000 kilometers per hour. Mars orbits at about 87,000 kilometers per hour. So both planets are constantly moving, constantly changing their positions relative to each other. To get from Earth to Mars, you have to use what is called a Hohmann transfer orbit. This is an elliptical path that takes advantage of the gravitational pull of the Sun to sling your spacecraft from Earth's orbit out to Mars's orbit. It is the most fuel-efficient way to make the trip, but it takes time, about 7 to 9 months, depending on the specific alignment of the planets. And here is the critical thing. This transfer orbit only works when Earth and Mars are in the right positions relative to each other. This alignment, this launch window, only opens once every 26 months. That is 2 years and 2 months. So if you miss your window, you have to wait another 26 months for the next one. This is not like missing a flight and catching the next one in a few hours. This is missing your window and being stuck wherever you are for over 2 years. Now, let us think about what this means for a Mars mission. You launch from Earth. 7 to 9 months later, you arrive at Mars. You land on the surface. Now what? Well, you cannot just turn around and fly back immediately, because Earth is no longer where it was when you left. It has moved in its orbit. To fly back, you need to wait until Earth and Mars are aligned again for a return transfer orbit. And that takes time. you will be on Mars for approximately 500 days, roughly a year and a half, before the return window opens. So the total mission duration from launch to landing back on Earth is approximately 2.5 to 3 years. 2.5 to 3 years away from Earth. Away from hospitals, away from rescue, away from resupply, away from everything and everyone you know. And this is the optimistic timeline. This assumes everything goes perfectly. If anything goes wrong, if the return rocket is not ready, if there is a medical emergency, if a critical system fails, then the astronauts miss their return window. And when that happens, they are stuck on Mars for another 26 months. Their supplies, which were calculated for a specific mission duration, now have to stretch for an additional 2+ years. Their radiation exposure continues to accumulate, their bodies continue to deteriorate, and the psychological burden of knowing they are trapped on an alien planet with no way home becomes almost unbearable. There is another aspect of distance that makes Mars qualitatively different from every other human space mission in history, and that is the communication delay. On the International Space Station, which orbits just 400 kilometers above Earth, communication with mission control is essentially instantaneous. Astronauts can have real-time conversations with doctors, engineers, family members. If something goes wrong, mission control can immediately analyze the situation, develop a solution, and talk the crew through it. On the Moon, the communication delay is about 1.3 seconds each way, barely noticeable. The Apollo astronauts could have near normal conversations with Houston. But Mars? The speed of light, which is the fastest anything can travel in the universe, takes between 4 and 24 minutes to cross the distance between Earth and Mars, depending on where the planets are in their orbits. That is 4 to 24 minutes one way. A round-trip communication, where you ask a question and receive an answer, takes 8 to 48 minutes. Think about what that means in an emergency situation. An astronaut on Mars has a medical crisis, a suit breach, a broken bone, a cardiac event. They radio Earth for help. The message takes, let us say, 15 minutes to reach Earth. Mission Control receives the message, assembles a team, analyzes the situation, develops a recommendation. That takes time, maybe 30 minutes if they are fast. They transmit their response. Another 15 minutes back to Mars. From the moment the astronauts sent their distress call to the moment they receive guidance from Earth, at least an hour has passed. In many medical emergencies, an hour is the difference between life and death. And it gets worse. Every 26 months, when the Sun passes directly between Earth and Mars during what is called solar conjunction, all communication is blocked entirely. Radio signals cannot pass through the Sun. The charged particles in the Sun's vicinity distort any signal that passes too close. This creates a complete communication blackout lasting approximately 2 weeks. 2 weeks during which the astronauts on Mars are completely on their own. No guidance from Mission Control, no conversations with family, no help of any kind. If a life-threatening emergency occurs during solar conjunction, the crew must solve it themselves or die. I want you to sit with that for a moment. Because this is fundamentally different from every other human experience in exploration. When Columbus crossed the Atlantic, he could not communicate with Spain, but he could still turn his ships around. When Shackleton was stranded in Antarctica, rescue was difficult, but not impossible. When the Apollo 13 crew had their oxygen tank explode, Mission Control worked the problem in real time and guided them home. None of these options exist on Mars. There is no turning around, there is no rescue mission, there is no real-time guidance. The astronauts on Mars will be, in every meaningful sense of the word, alone. More alone than any human being has ever been in the history of our species. And their aloneness is not a temporary condition that will be resolved in a few days or weeks. It is a permanent state that will last for the entire duration of their mission, which, as we discussed, is measured in years. Now, I know we have been talking a lot about distance and time, and you might be thinking, okay, I understand Mars is far away, But surely the actual danger is not just the distance, right? The danger has to be about what happens when you get there. And you are absolutely right. But here is what most people do not realize. The danger does not start when you arrive at Mars. The danger starts the moment you leave Earth. In fact, the 7-month journey to Mars is itself one of the most dangerous phases of the entire mission. And the reason comes down to one word that should terrify anyone who dreams of interplanetary travel. Radiation. Cosmic radiation. The invisible, silent, relentless killer of deep space. Here on Earth, we are protected from most space radiation by two incredible natural shields. The first is Earth's magnetic field, also called the magnetosphere. Our planet's molten iron core generates a powerful magnetic field that extends thousands of kilometers into space, creating a protective bubble that deflects most of the charged particles streaming toward us from the sun and from deep space. The second shield is our atmosphere. Earth's thick blanket of air, which is about 100 kilometers deep, absorbs and scatters the high-energy particles that make it past the magnetic field. Together, these two shields reduce the radiation we experience on Earth's surface to about 2.4 millisieverts per year from natural background sources. That is a tiny, harmless amount. Your body can handle it easily. Your cells have evolved over billions of years to repair the minor DNA damage caused by this level of radiation. But the moment you leave Earth's protective embrace, the moment you pass beyond the magnetosphere and enter the void of interplanetary space, those shields disappear. And you are exposed to the full, unfiltered fury of cosmic radiation. There are two main types of radiation in deep space that will attack Mars-bound astronauts. The first is solar particle events, or SPEs. These are sudden, violent bursts of high-energy protons ejected by the sun during solar flares and coronal mass ejections. A major solar particle event can deliver a potentially lethal dose of radiation in just a few hours. The particles come fast, they come hard, and they come with very little warning. On Earth, we barely notice solar flares because our magnetosphere and atmosphere absorb them. In deep space, there is nothing between you and the full force of the sun's wrath. During a major solar event, astronauts would need to immediately retreat to a specially shielded storm shelter within their spacecraft. But here is the problem. Heavy shielding adds weight. Weight adds cost. And the rocket equation, which we will discuss in detail later, means that every kilogram of shielding requires additional fuel, which requires additional shielding for the fuel, which requires more fuel, in an endless spiral of increasing mass and cost. So spacecraft will have limited shielding, and storm shelters will be small, cramped spaces where the crew huddles together during the worst solar storms, hoping the walls are thick enough to stop the particles from cooking their cells. The second type of radiation is even more terrifying, because there is essentially no way to stop it. Galactic cosmic rays, or GCRs, these are high-energy particles, mostly protons and atomic nuclei, that originate from outside our solar system. They come from the explosions of massive stars, supernovae, events so energetic that they accelerate particles to nearly the speed of light. These galactic cosmic rays have been traveling through the galaxy for millions of years, and they carry enormous amounts of energy. So much energy that they can pass through the walls of a spacecraft as if the walls were not even there. They pass through spacesuits, they pass through human flesh, they pass through bone, and as they pass through your body, they leave a trail of destruction. A single galactic cosmic ray particle hitting a strand of your DNA can cause a double strand break, the most dangerous type of DNA damage. Your cells have repair mechanisms for this, but the repair is not always perfect. Sometimes the cell repairs itself incorrectly, leading to mutations. And mutations, accumulated over time, lead to cancer. But it gets even worse. When a high-energy cosmic ray hits an atom in the wall of your spacecraft, or in your body, it does not just pass through cleanly. It shatters the atom, creating a shower of secondary particles, neutrons, protons, heavy ions, that spray out in all directions, causing even more damage. This is called a nuclear spallation event, and it means that even shielding can be counterproductive in some cases. Thick metal walls can actually create more secondary radiation than they block. It is a deeply frustrating problem. You cannot hide from galactic cosmic rays. You cannot shield against them effectively with current technology. And they are constant. Unlike solar particle events, which come in bursts, galactic cosmic rays are always there, a steady rain of high-energy destruction falling on you every second of every day for the entire duration of your mission. NASA estimates that a round-trip Mars mission would expose astronauts to approximately 1,000 millisieverts of radiation. To put that in context, the annual radiation dose limit for a nuclear power plant worker on Earth is 50 millisieverts. A Mars mission gives you 20 times the annual limit for someone who works with radiation for a living, and you get it in a single trip. The health consequences of this level of exposure are severe and well documented. Cancer risk increases significantly, with some estimates suggesting a 5 to 10% increase in the lifetime probability of developing a fatal cancer. But cancer is not the only concern. High-energy radiation damages the cardiovascular system, increasing the risk of heart disease. It damages the central nervous system, potentially causing cognitive decline, memory loss, reduced motor function, and changes in behavior and mood. It causes cataracts by damaging the lens of the eye. It suppresses the immune system, making astronauts more vulnerable to infections and less able to heal from injuries. And some of these effects are not just long-term. They can manifest during the mission itself, when the crew is already dealing with 100 other challenges and has no access to advanced medical care. The European Space Agency has called radiation the showstopper for Mars exploration. That word, showstopper, is not used lightly in the engineering world. It means a problem so severe that it could prevent the mission from happening at all. Some researchers have gone even further. A study published in recent years estimated that a Mars mission could carry a mortality rate of up to 50% due to radiation exposure alone. 50%. That means if 6 astronauts go to Mars, 3 of them might develop fatal conditions as a direct result of radiation. And here is perhaps the most chilling detail about space radiation. Astronauts have reported a bizarre phenomenon during deep space missions. They see flashes of light even when their eyes are closed, even in complete darkness. These are called cosmic ray visual phenomena, or more colloquially, the astronaut's eye effect. What is happening is that individual cosmic ray particles are passing through their eyeballs and interacting with the retinal cells, creating brief flashes of perceived light. It is like a personal miniature fireworks show happening inside your skull. Except those same particles that are tickling your retina are also passing through your brain, your heart, your bones, your organs, damaging cells along the way. Every flash of light an astronaut sees with their eyes closed is a reminder that they are being irradiated by the universe itself, and there is nothing they can do about it. And radiation is just the beginning of what happens to the human body during the journey to Mars. Because the 7-month trip takes place in microgravity, in the weightlessness of space. And microgravity does terrible things to the human body. We evolved on Earth under the constant pull of 1 g of gravity. Every system in our body, from our bones to our muscles to our cardiovascular system to our eyes, developed under and depends on this gravitational force. Take it away, and the body begins to break down with alarming speed. Let us start with bones. On Earth, your bones are constantly being remodeled, old bone is broken down and new bone is built up, in a process mediated by the mechanical stress of supporting your weight against gravity. In microgravity, there is no weight to support. The bones sense that they are not needed at their current density, and the body begins to dissolve them. Astronauts in space lose approximately 1 to 1.5% of their bone mineral density per month. That might not sound like much, but over a 7-month journey to Mars, that is 7 to 10% of bone density lost, mostly from weight-bearing bones like the hips, spine, and legs. This is essentially accelerated osteoporosis. The bones become weaker, more brittle, more prone to fracture. and the calcium released from the dissolving bones floods the bloodstream, increasing the risk of kidney stones, an excruciatingly painful condition that, in the absence of proper medical facilities, could become life-threatening. Then there are the muscles. Without gravity, the muscles that normally work to support your posture and move your body against gravitational resistance begin to atrophy. Leg muscles, back muscles, core muscles, they all begin to waste away. Astronauts on the International Space Station exercise vigorously for at least 2 hours every day using specially designed resistance machines and treadmills with bungee cord harnesses, and they still lose muscle mass. Over a 7-month journey, astronauts can lose up to 20% of their muscle mass if countermeasures are not perfectly maintained. And the heart, which is itself a muscle, is not immune. In microgravity, the heart does not have to work as hard to pump blood because there is no gravity pulling blood downward. So the heart, like any muscle that is not being challenged, begins to weaken and atrophy. Studies have shown that the heart actually changes shape in microgravity, becoming more spherical instead of its normal elongated form. Cardiac output decreases. Blood volume drops. The cardiovascular system becomes deconditioned, which means it loses its ability to respond to the demands of gravity. This will become critically important when the astronauts arrive at Mars and suddenly experience gravity again, even the reduced gravity of Mars. Now, there is a phenomenon that I find particularly disturbing, and it is one of NASA's top health concerns for long-duration spaceflight. It is called Spaceflight-Associated Neuroocular Syndrome, or SANS. Here is what happens. In microgravity, the fluids in your body, which on Earth are pulled downward by gravity, redistribute evenly throughout your body. This means more fluid shifts upward, into your chest and head. Your face puffs up. Your sinuses become congested. Astronauts on the ISS often look like they have perpetual head colds, with puffy faces and stuffy noses. But the fluid shift does something much more serious than make you look puffy. The increased fluid pressure in the head raises intracranial pressure, the pressure inside your skull. This elevated pressure pushes on the back of your eyeballs, literally flattening them. It causes the optic disc, where the optic nerve meets the retina, to swell. And the result is vision degradation. Astronauts develop farsightedness, difficulty focusing on nearby objects, blurriness, and in some cases permanent changes to their visual acuity. Approximately 70% of long-duration astronauts develop some form of SANS. 70%. That is not a rare side effect. That is a near-universal consequence of extended spaceflight. Now imagine you are an astronaut arriving at Mars after 7 months of microgravity exposure. You need to land a spacecraft. You need to operate complex equipment. You need to navigate an alien landscape. And your vision is degraded. You might not be able to read instrument panels clearly. You might misjudge distances. You might struggle with the fine motor tasks required to maintain your life support systems. And there is no ophthalmologist on Mars. There is no corrective surgery available. You just have to deal with it. I want to talk about one more thing that happens during the journey. Something that does not get as much attention as radiation or bone loss, but might be just as dangerous. The psychological effects of the transit phase. 7 months in a spacecraft. Let us think about what that really means. The habitable volume of a Mars-bound spacecraft will be, by even the most optimistic estimates, comparable to a small apartment, maybe the size of a modest 2-bedroom flat. And in that space, 4 to 6 people will live, work, sleep, eat, exercise, and exist for 7 continuous months. There is no going outside for a walk. There is no opening a window for fresh air. There is no visiting a friend. There is no solitude, because your crewmates are always there, always within arm's reach, always making noise, always present. And there is no escape. On the ISS, astronauts serve 6-month rotations, and they know every single day that they could look out the window and see Earth right there, a beautiful blue marble, just 400 kilometers below. They could be home in a matter of hours if needed. A Soyuz or Crew Dragon capsule is always docked at the station, ready for emergency evacuation. Mars-bound astronauts have none of these psychological anchors. They cannot see Earth as a reassuring presence outside their window. As the weeks pass, Earth shrinks. It goes from being a recognizable planet to a bright star to a faint point of light indistinguishable from all the other stars. And with every passing day, the finality of their decision becomes more concrete. They are moving farther from home than any human being has ever been. And they cannot turn back. Studies of people in extreme isolation, Antarctic winter over cruise, submarine deployments, simulated Mars missions like Russia's Mars 500 experiment consistently show a pattern of psychological effects. In the first phase, there is excitement and novelty. Everything is new and interesting. Crew morale is high. But as weeks turn into months, the novelty fades and the reality of confinement sets in. Irritability increases, sleep patterns become disrupted because there is no natural day-night cycle in space to regulate circadian rhythms. Small annoyances that would be trivial on Earth become sources of intense friction. The way a crewmate chews their food, the sound of someone's breathing at night, a disagreement about the thermostat setting. These petty irritations compound over time, building into genuine interpersonal conflicts that can fracture crew cohesion. In the Mars 500 experiment, where 6 volunteers were sealed in a mock spacecraft for 520 days to simulate a Mars mission, researchers observed disturbed sleep cycles, reduced physical activity, depressive symptoms, and periods of hypoactivity where crew members essentially withdrew from participation. And this was a simulation. The volunteers knew they were in Moscow. They knew that in a real emergency they could walk out the door. On a real Mars mission, there is no door, there is no exit. There is just the ship, your crewmates, and 200 million kilometers of nothing. Psychologists have identified something called the third quarter phenomenon, a predictable dip in morale and performance that occurs approximately 3/4 of the way through any long-duration isolated mission. At this point, the initial excitement has long since faded. The end is not yet in sight, and the cumulative weight of confinement, monotony, and isolation reaches its peak. People become more prone to depression, anxiety, cognitive errors, and interpersonal conflict during this period. On a 7-month Mars transit, the third quarter phenomenon would hit around month 5, when the astronauts are deep in the void between the planets, too far from Earth for comfort, too far from Mars for excitement. It is a psychological no man's land, and navigating it successfully will require extraordinary mental resilience from the crew. And there is one more psychological factor that I think is the most profound and the least discussed. It is the knowledge, the deep, unavoidable knowledge that you might not be coming back. Every previous space mission in human history has been conducted with the expectation of return. Even the most dangerous missions, Apollo 13, the early space shuttle flights, the earliest orbital missions, were designed with return as the plan. The crew knew the risks, but they also knew that the full power of NASA and the world's engineering capability was focused on bringing them home. Mars astronauts will not have that assurance. They will know, because they will have been briefed in exhaustive detail, that the return trip depends on technologies that have never been proven at scale. That the fuel for their return must be manufactured on Mars from local resources, a process that has only been demonstrated in tiny proof-of-concept experiments. That their bodies will be weakened by months of microgravity and radiation exposure. That any one of 100 possible failures could strand them on Mars permanently. They will carry this knowledge with them every minute of every day, from the moment they leave Earth until the moment they either step foot back on our planet or accept that they never will. And this kind of existential burden, this awareness of potential permanent separation from everything and everyone you have ever known, is something no human being has ever had to carry before. But let us move on, because the journey is just the first act of this drama. The second act begins when the spacecraft arrives at Mars, and this is where things get truly harrowing. You see, landing on Mars is one of the most terrifyingly difficult things in all of aerospace engineering. NASA calls it the 7 minutes of terror, and that is not a dramatic exaggeration. It is a coldly accurate description of the entry, descent and landing phase, or EDL, during which a spacecraft must decelerate from interplanetary speeds of around 20,000 kilometers per hour to nearly zero, and it must do so in roughly 7 minutes, completely autonomously, with no help from Earth. Because remember the communication delay? By the time a signal from the landing spacecraft reaches Earth and a response is sent back, the landing is already over. It has either succeeded or failed. The spacecraft, and everyone on it, is either safely on the surface or scattered across a Martian crater in pieces. Here is why landing on Mars is so uniquely difficult. Mars has what engineers call the worst atmosphere in the solar system for landing. It is too thin to be useful, but too thick to ignore. Earth's atmosphere is dense and thick, about 101,000 pascals of pressure at sea level. When a spacecraft re-enters Earth's atmosphere, it can use atmospheric drag to slow down significantly. Parachutes deploy and work beautifully because there is enough air for them to grab onto. Mars's atmosphere, by contrast, has a surface pressure of only about 600 pascals. That is less than 1% of Earth's atmospheric pressure. It is barely there, and yet it is there, which means a spacecraft entering Mars's atmosphere at 20,000 kilometers per hour will experience extreme frictional heating. The heat shield will reach temperatures of thousands of degrees, so Mars's atmosphere is thick enough to try to burn you up, but too thin to slow you down. It is the worst of both worlds. A cosmic booby trap, parachutes, which work beautifully on Earth, are far less effective on Mars because there is so little air for them to work with. They help, but they cannot do the job alone, especially for large, heavy payloads. And here is the critical problem. Everything we have ever landed on Mars has been relatively small and light. The Perseverance rover, the largest and heaviest object ever successfully landed on Mars, has a mass of about 1 metric ton, 1,000 kilograms. That is roughly the weight of a small car. To land humans on Mars, we need to put down vehicles weighing between 50 and 100 metric tons. That is 50 to 100 times heavier than anything we have ever landed there, and we do not have a proven method for doing this. Let me say that again, because it is important. As of right now, we do not have a proven, tested, validated method for landing a human-scale vehicle on Mars. The parachute and sky crane system used by Perseverance is at its engineering limit. It cannot be scaled up enough to handle the masses required for a human mission. This is not a minor gap. This is a fundamental, unsolved engineering problem. Now, there are potential solutions being developed, and I want to be fair about that. In 2022, NASA successfully tested LOFTID, the low Earth orbit flight test of an inflatable decelerator. This is essentially a giant inflatable heat shield that deploys during atmospheric entry, creating a much larger surface area to generate more drag in the thin Martian atmosphere. Think of it like an enormous inflatable mushroom cap that pops open around the spacecraft, dramatically increasing its air resistance. The test was conducted in Earth's upper atmosphere, which has a density similar to Mars's atmosphere near the surface, and it worked. This is promising. Then there is supersonic retropropulsion, or SARP. This is the idea of firing the spacecraft's rocket engines forward, against the direction of travel, while the vehicle is still moving at supersonic speeds through the atmosphere. For years, aerodynamics experts were skeptical of this approach. The concern was that firing engines into an oncoming supersonic airflow would create unstable shockwaves that could batter and potentially destroy the vehicle. The mathematics were too complex to model with confidence. But then, something unexpected happened. SpaceX started landing its Falcon 9 first-stage boosters back on Earth, and during the landing burns, the boosters fire their engines retrograde at supersonic speeds through the upper atmosphere. NASA's Jet Propulsion Laboratory asked SpaceX if they could study the data from these landings, and what they discovered was remarkable. The exhaust plume from the engines creates a kind of protective bubble around the vehicle, a shock front that actually insulates the spacecraft from both the aerodynamic buffeting and some of the heating. It was new physics that nobody had predicted. Rob Manning, the chief engineer at JPL, who has led entry, descent and landing for several Mars missions, described it with cautious optimism, noting that while several technical issues still need to be resolved, the fundamental physics appear to work in their favour. But optimism and proof are different things. Neither lofted nor supersonic retropropulsion has been tested on Mars. Neither has been tested at the scale required for a human mission. And Mars gives you exactly one chance. There is no practice run. There is no abort option during EDL. You either execute perfectly or you die. And here is a sobering piece of context. The historical success rate for Mars landing missions is roughly 50%. About half of all spacecraft sent to land on Mars have failed. Mars Polar Lander in 1999 crashed because its engines shut down prematurely when its landing sensors gave a false signal. The Beagle 2 lander in 2003 reached the surface, but its solar panels failed to deploy, and it was never heard from again. The Schiaparelli lander in 2016 crashed into Mars at 540 km per hour because a computer glitch during descent caused it to think it was below the surface when it was still nearly 4 kilometers up, causing it to shut off its braking systems prematurely. These were robotic missions. Machines, if they crash, we lose data and money. But on a crewed mission, a failure during entry, descent and landing means human beings are killed. And they are killed on live television in front of the entire world, 225 million kilometers from the nearest help. I want you to think about something else during this landing phase. The astronauts who are about to attempt this landing have just spent 7 months in microgravity. Their muscles have atrophied. Their bones have weakened. Their cardiovascular systems are deconditioned. Their vision may be impaired from SANS. They are fatigued. They have been exposed to months of cosmic radiation, and now, in the span of 7 minutes, they must survive forces of several Gs as the spacecraft decelerates from interplanetary speeds. G-forces that will press down on bones that have lost 10% of their density. G-forces that will squeeze a heart that has spent 7 months barely working. And if they survive the landing, they must then immediately begin functioning on the surface of Mars, setting up habitats, deploying equipment, beginning the tasks that will keep them alive. There is no recovery period. There is no 2-week rest cure. Mars does not wait for you to feel better. Now we arrive at Mars itself. The surface. The destination. The place that has captivated human imagination for centuries. And I need to prepare you for something, because the reality of Mars as a place to live is so starkly different from the romanticized image in popular culture that it might shock you. Mars is not a slightly chilly, slightly dusty version of our Arizona desert. Mars is, without exaggeration, one of the most hostile environments in the known solar system for human life. It is a place that is actively trying to kill you in at least half a dozen different ways simultaneously, every second of every day. And I want to go through each of these threats in detail, because understanding them is essential to understanding why returning from Mars is so problematic. Let us start with the atmosphere, or more accurately, the lack of one. Mars's atmosphere is composed of approximately 95.3% carbon dioxide, 2.7% nitrogen, 1.6% argon, and trace amounts of oxygen and other gases. The oxygen content is 0.13%. On Earth, the air we breathe is about 21% oxygen. So Mars's atmosphere has less than 1/100th the oxygen concentration of Earth's. You cannot breathe it. Even if you could somehow extract the tiny amount of oxygen present, the atmospheric pressure on Mars is so low that it would not matter. Mars's surface atmospheric pressure is approximately 600 pascals. Earth's sea level atmospheric pressure is 101,325 pascals. Mars has less than 1% of Earth's atmospheric pressure. This is below what is called the Armstrong limit, the pressure at which water boils at body temperature. What does that mean in practical terms? It means that if you stepped outside on Mars without a pressure suit, the warm fluids on the surface of your body, the moisture on your tongue, the tears in your eyes, the saliva in your mouth would begin to boil. Not because they are hot, but because the pressure is so low that the boiling point of water drops below body temperature. Your lungs, which evolved to operate at Earth atmospheric pressure, would not be able to function. The gas in your lungs would expand rapidly. If you tried to hold your breath, your lungs could rupture. Dissolved gases in your blood would begin to form bubbles, a condition called ebulism, similar to what happens to deep sea divers who ascend too quickly. Within 10 to 15 seconds, you would lose consciousness. Within 1 to 2 minutes, you would be dead. Not from suffocation, not from cold, but from the simple fact that Mars's atmosphere is too thin for a human body to function. And even inside a pressurized habitat or spacesuit, the atmosphere poses challenges. The carbon dioxide concentration means that any breach, any crack in a habitat seal, any failure in a suit's pressure system would allow deadly carbon dioxide to seep in. Carbon dioxide is an insidious poison. At low concentrations, it causes headaches, dizziness, and difficulty concentrating. At higher concentrations, it causes confusion, loss of consciousness, and death. The life support systems inside a Mars habitat would need to constantly scrub carbon dioxide from the air, generate oxygen, and maintain Earth-like atmospheric pressure and composition. These systems would need to operate flawlessly, 24 hours a day, 7 days a week, for the entire duration of the mission. A failure in the CO2 scrubbing system, even for a few hours, could be fatal. Now let us talk about temperature. Mars is cold. Not just a little cold, not winter in Minnesota cold. Mars is cold in a way that is almost incomprehensible to human experience. The average surface temperature on Mars is about negative 60 degrees Celsius, which is negative 80 degrees Fahrenheit. But that average hides extreme variation. At the equator, during the peak of summer, temperatures can reach a relatively balmy 20 degrees Celsius, about 68 degrees Fahrenheit. That sounds almost pleasant, right? But wait, on the same spot, the same day, when the sun goes down, the temperature can plummet by 80 or more degrees. The nighttime temperature at the equator can drop to negative 73 degrees Celsius. That is a daily temperature swing of nearly 100 degrees Celsius. Your habitat, your equipment, your spacesuit, everything must be designed to handle this thermal cycling, expanding in the warmth of the day and contracting in the cold of the night, over and over, for years. Metal fatigue from thermal cycling is a real engineering concern. Materials that work perfectly in stable temperatures can crack, warp, and fail under repeated extreme temperature changes. And at the poles during winter, temperatures drop to negative 153 degrees Celsius. That is negative 243 degrees Fahrenheit. At those temperatures, carbon dioxide freezes out of the atmosphere and falls as dry ice snow. The coldest temperature ever recorded on Earth at the Vostok station in Antarctica was negative 89.2 degrees Celsius. Mars regularly gets 60 degrees colder than the coldest place on Earth. If your heating system fails on a Martian night, if your habitat loses power for even a few hours during the cold season, the interior temperature will drop with terrifying speed. Hypothermia would set in rapidly, frostbite would follow, and death from exposure would come not long after. In the most extreme cold, even the materials of your habitat could become brittle and fail, as metals and polymers lose their flexibility and structural integrity at very low temperatures. Next, I want to talk about something that genuinely frightens me, and that is the Martian soil. We call it regolith, the layer of loose rock and dust that covers the Martian surface. And this regolith is not just dirt, it is, in many ways, toxic waste. Mars's soil is rich in perchlorate compounds, chemicals that contain chlorine and oxygen in a highly reactive configuration. Perchlorates were discovered on Mars by the Phoenix lander in 2008, and subsequent measurements by Curiosity and other missions have confirmed that they are present across the entire planet at concentrations of approximately 0.5 to 1% by weight. Now, perchlorates are not exotic chemicals. They are used on Earth in rocket fuel, fireworks, and as industrial chemicals. We know a lot about what they do to the human body, and what they do is not good. Perchlorates interfere with the thyroid gland's ability to absorb iodine. The thyroid needs iodine to produce hormones that regulate metabolism, growth, and development. When perchlorates block iodine absorption, the thyroid cannot function properly, leading to hypothyroidism, a condition that causes fatigue, weight gain, depression, cognitive impairment, and in severe cases, a life-threatening condition called myxedema coma. On Earth, perchlorate contamination in water at concentrations as low as a few parts per billion is considered a health concern. On Mars, perchlorates are present in the soil at parts per thousand. That is millions of times higher than what we consider safe on Earth. But the perchlorate problem is not just about chemical toxicity. The Martian dust itself is physically dangerous. The particles are extremely fine, averaging about 3 micrometers in diameter. That is small enough to be inhaled deep into the lungs, past the body's normal filtering mechanisms in the nose and upper airways. Once in the lungs, these ultrafine particles can cause irritation, inflammation, and over time scarring of the lung tissue, a condition known as pulmonary fibrosis. Pulmonary fibrosis is progressive and irreversible. It reduces the lung's ability to exchange oxygen and carbon dioxide, leading to increasing breathlessness and eventually respiratory failure. And the Martian dust does not stay outside. Lunar dust was one of the biggest surprises of the Apollo program. Despite their best efforts, astronauts could not prevent moon dust from getting inside their spacecraft and habitats. It coated everything. It got into equipment. It irritated eyes and respiratory systems. Apollo astronaut Harrison Schmitt reported what he called lunar hay fever from dust exposure. Martian dust will be even worse, for 2 reasons. First, it contains those toxic perchlorates. Second, it is both magnetic and electrostatic. The iron oxide content of Martian dust, which is what gives Mars its characteristic red color, makes the dust magnetically sticky. And the low humidity and constant wind on Mars create electrostatic charges that make the dust cling to surfaces with tenacious grip. It will coat spacesuits. It will coat solar panels. It will find its way into habitat airlocks, into equipment joints, into ventilation systems. And once inside, it will be inhaled by astronauts, absorbed through skin, and ingested through contaminated food and water. Long-term exposure to perchlorate-laced Martian dust could cause thyroid dysfunction, lung disease, and potentially cancer. And there is no way to completely prevent exposure. You can minimize it, you can filter it, but living and working on Mars means living and working in perchlorate-contaminated dust. Every single day. Now we need to discuss radiation on the surface of Mars, because it is a completely different threat than the radiation experienced during the transit phase, and it does not get better when you land. In fact, in some ways, it gets worse. You see, Earth's magnetic field and thick atmosphere together reduce the radiation dose at the surface to negligible levels. Mars has neither a meaningful magnetic field nor a thick atmosphere. Mars lost its global magnetic field approximately 4 billion years ago, when its core cooled, and the internal dynamo that generated the field shut down. Without a magnetic field, there is nothing to deflect the charged particles from the Sun and from deep space, and Mars's atmosphere, as we have discussed, is less than 1% as dense as Earth's. It provides almost no radiation shielding. The result is that the Martian surface is bathed in radiation at levels that would be considered a serious health hazard by any standard on Earth. Measurements from the Curiosity rover's radiation assessment detector have determined that the surface radiation dose on Mars is approximately 0.67 millisieverts per day. That might not sound like much, but let us put it in context. On Earth's surface, the natural background radiation dose is about 0.01 millisieverts per day. Mars surface radiation is 67 times higher than Earth's surface radiation. Every single day. Over a 500-day surface stay, which is the minimum time between transfer windows, astronauts would accumulate approximately 335 millisieverts of radiation just from being on the surface. Added to the approximately 300 millisieverts from the 7-month outbound journey, the total exposure is already over 600 millisieverts before they even think about the return trip. And the return trip adds another 300 millisieverts, bringing the total mission dose to approximately 1,000 millisieverts or more. That is one full sievert. One full sievert of radiation increases the lifetime cancer risk by approximately 5% and causes measurable damage to nearly every organ system in the body. But the daily background radiation is not the only concern. Solar particle events, those sudden bursts of radiation from solar flares and coronal mass ejections, pose an acute threat on the Martian surface, just as they do in deep space. Because Mars has no magnetosphere, these solar storms hit the surface directly. On Earth, a massive solar flare is a spectacle, producing beautiful auroras at the poles, but causing no direct harm to people. On Mars, the same solar flare could deliver a lethal radiation dose to anyone caught outside their habitat without adequate shielding. And solar storms can hit with as little as 15 to 30 minutes of warning. If an astronaut is on an EVA, a spacewalk on the Martian surface, when a major solar particle event begins, they might not have time to get back to the habitat. They would be caught in the open with only their spacesuit for protection, as a wave of high-energy protons slams into them. Depending on the severity of the event, this could cause acute radiation sickness, with symptoms including nausea, vomiting, fatigue, skin burns, immune suppression, and in extreme cases, death within days or weeks. I cannot emphasize this enough. Radiation on Mars is not a theoretical risk. It is not a minor concern to be managed with sunscreen and good luck. It is a constant, pervasive, potentially lethal threat that will be with the astronauts every moment they are on the planet, and there is no way to eliminate it. You can only try to reduce it. And the best methods for reducing it? Underground habitats, heavy shielding, limited surface exposure, all come with their own costs and complications that add to the already overwhelming challenge of surviving on Mars. Let us talk about dust storms, because Mars has weather, and Mars's weather can be absolutely apocalyptic. Mars experiences dust storms of a scale that has no parallel on Earth. Small, localized dust storms happen frequently, kicking up dust that reduces visibility and coats equipment. But periodically, roughly every few Mars years, these local storms grow and merge and expand until they engulf the entire planet. These global dust storms can last for months, wrapping Mars in a thick blanket of suspended dust that blocks out the sun. In 2018, a global dust storm on Mars grew so large and so opaque that it effectively killed NASA's Opportunity rover. Opportunity, which had been operating on Mars for nearly 15 years, ran on solar power. When the global dust storm hit, sunlight at the surface dropped by up to 99%. Opportunity's solar panels could not generate enough power to keep the rover warm, and its batteries died. NASA tried for months to re-establish contact after the storm cleared, but the rover never responded. It was declared dead in 2019. Now think about what a global dust storm means for a human mission. If the mission relies on solar power, as most Mars habitat designs do, a global dust storm could reduce power generation by up to 99% for weeks or months. That means reduced heating, reduced oxygen generation, reduced water recycling, reduced food production lighting, reduced communication capability. Everything that keeps you alive runs on power, and a global dust storm can effectively cut off your power supply. This is why many Mars mission designers are now advocating for nuclear power systems instead of, or in addition to, solar panels. small nuclear reactors or radioisotope thermoelectric generators could provide steady, reliable power regardless of dust conditions. But nuclear power systems for Mars have their own challenges. They are heavy, expensive, complex, and have never been tested on Mars. NASA's Killer Power project is working on small nuclear reactors suitable for Mars, but they are still in development. And even with nuclear power, dust storms create other problems. Visibility drops dramatically, making surface operations dangerous or impossible. The electrostatic properties of the dust can interfere with electronics, and the fine dust particles laden with perchlorates get into everything. Perhaps you might be thinking at this point, well, sure, Mars is harsh, but could not astronauts just stay inside their habitat for the duration of a dust storm and wait it out? Theoretically, yes, but imagine being inside a small habitat, already confined, already isolated, and then having the sky go dark for months. The psychological effect of this would be devastating. You are already on an alien planet, far from home, possibly dealing with health issues from radiation and microgravity. And now the lights go out. The windows show nothing but swirling red darkness. Your power systems are strained, you are rationing energy, and you have no idea when the storm will end. Days? Weeks? Months? The longest global dust storm on record lasted approximately 4 months. Imagine 4 months of darkness, confinement, and power rationing on top of everything else. The psychological toll would be immense. Now I want to address something that is often overlooked in discussions about Mars missions, and that is the gravity question. Mars has a surface gravity of about 3.72 meters per second squared, which is approximately 38% of Earth's gravity. So a person weighing 80 kilograms on Earth would weigh only about 30 kilograms on Mars. This sounds like it could be fun, right? Bouncing around, feeling light, jumping higher than you ever could on Earth. But the reality is far more concerning. You see, we have extensive data on what happens to the human body in 2 gravitational conditions, 1g, which is Earth's gravity, and approximately 0g, which is the microgravity of the International Space Station. We know that 1g is fine because we evolved in it. We know that 0g is terrible because of all the bone loss, muscle atrophy, cardiovascular deconditioning, and SANS that we discussed earlier. But Mars gravity? At 0.38g? We have absolutely no data. None. No human being has ever experienced sustained 0.38g. We have no animal studies in 0.38g. We have no cell biology studies in 0.38g. We simply do not know what it does to the human body over months and years. And this is one of the biggest unknowns in all of Mars mission planning. Is 0.38g enough gravitational stimulus to prevent or slow down bone loss? We do not know. Is it enough to maintain muscle mass? We do not know. Is it enough to keep the cardiovascular system conditioned? We do not know. Is it enough to prevent SANS? We do not know. The answer might be yes. 0.38g might be enough to keep the body reasonably healthy. In that case, astronauts on Mars would be in much better shape than astronauts on the ISS who spend months in near-zero gravity. But the answer might also be no. 0.38g might not be enough. In that case, astronauts on Mars would continue to lose bone density, continue to lose muscle mass, continue to experience cardiovascular deconditioning, just at a slower rate than in microgravity. And if that is the case, then the longer you stay on Mars, the weaker you get. And the weaker you get, the harder it becomes to perform the physically demanding tasks of surviving on Mars and preparing for a return trip. It creates a vicious cycle. Mars gravity weakens you, and your weakness makes it harder to escape Mars gravity. And here is the truly terrifying implication of this. If Mars gravity is not sufficient to maintain human health, then an astronaut who spends 500 or more days on Mars on top of 7 months of microgravity transit may have a body so deteriorated that returning to Earth's full 1G gravity would be medically catastrophic. Their bones, weakened by over a year and a half of reduced gravitational stimulus, might not be strong enough to support their weight on Earth. The simple act of standing up could cause compression fractures in their spine. Walking could fracture their hips. Their heart, after 18 months of pumping blood in reduced gravity, might not be strong enough to maintain blood pressure against Earth's gravitational pull. They could faint upon standing. They could experience cardiac arrhythmias. Their muscles, atrophied from over a year of reduced loading, might not have the strength to support basic movement. Essentially, if Mars gravity is not protective enough, then astronauts who land on Mars become physiologically incompatible with Earth. Their body adapts to Mars, and in doing so, loses the ability to function on their home planet. They become Martians, in the most literal, most tragic sense of the word. Let us now turn to what I believe is the absolute core of this entire video's thesis. The return trip. This is the section where everything we have discussed comes together into a single, overwhelming argument for why returning from Mars may be impossible, at least with current and near-future technology. Because the return trip is not just one problem. It is a cascading series of problems, each one feeding into and amplifying the others, creating a challenge so formidable that it makes the outbound journey look like a leisurely cruise by comparison. And the first, and perhaps most fundamental of these problems, is fuel. Getting off the surface of Mars requires fuel. A lot of fuel. Even though Mars has a lower gravity than Earth, its escape velocity is still 5.03 kilometers per second. That is lower than Earth's escape velocity of 11.2 kilometers per second, but it is still enormous. You need a powerful rocket with a large amount of propellant to reach that velocity and escape Mars's gravitational pull. And here is where we run into one of the most fundamental and unforgiving laws of physics in all of rocketry. The Tsiolkovsky rocket equation. I will spare you the mathematics, but the essence of it is this. The more massive your payload, the more fuel you need to accelerate it to a given velocity. But fuel itself has mass, so you need fuel to carry the fuel. And you need fuel to carry the fuel that carries the fuel. It is an exponential relationship that makes every additional kilogram of payload horrifically expensive in terms of fuel. For a Mars return mission using methane and liquid oxygen as propellant, which is the baseline plan for SpaceX's Starship, you need approximately 1,200 metric tons of propellant. 1,200 metric tons. That is 1,200,000 kilograms of fuel. Just for the return trip. There is absolutely no way to carry that amount of fuel from Earth to Mars. The mass penalty would make the entire mission impossible. The spacecraft would be too heavy to launch from Earth. So the only viable option, the plan that every serious Mars mission architecture relies on, is to manufacture the fuel on Mars. This concept is called in situ resource utilization, or ISRU. The basic idea is elegant. Mars's atmosphere is 95% carbon dioxide. If you can extract carbon dioxide from the atmosphere and combine it with hydrogen, using a chemical process called the Sabatier reaction, you get methane and water. The methane is your fuel. Electrolyze the water and you get hydrogen, which you recycle back into the process, and oxygen, which serves as your oxidizer. Fuel and oxidizer, manufactured on Mars from local resources, without having to bring them from Earth. It sounds brilliant, and in principle it works. NASA demonstrated this with the MOXIE instrument on the Perseverance rover. MOXIE, the Mars Oxygen in Situ Resource Utilization Experiment, successfully extracted oxygen from the Martian atmosphere. It produced about 12 grams of oxygen per hour. That is roughly enough for one person to breathe for about 10 minutes. The experiment was a proof of concept, and it worked. But proof of concept and industrial scale production are very, very different things. To fuel a return Starship, you would need to produce approximately 1,200 metric tons of propellant. If you have 2 years to do it, which is roughly the time between transfer windows, That requires producing approximately 1,600 kilograms of propellant per day. Every day. For 2 years straight. Without interruption. Let us think about what that requires. You need a massive chemical processing plant on the surface of Mars. You need compressors to suck in and pressurize Mars's thin atmosphere. You need electrolysis systems to split water into hydrogen and oxygen. You need the Sabatier reactor to combine hydrogen and carbon dioxide into methane and water. You need cryogenic systems to liquefy the methane and oxygen and store them at extremely low temperatures. You need enormous tanks to hold 1,200 metric tons of propellant. You need a reliable, high-capacity power source to run all of this. Every single one of these systems has to work on Mars. In the dust. In the extreme cold. In the radiation. With no possibility of spare parts being shipped from Earth on short notice. And if anything in this chain breaks, if the compressor fails, if the electrolysis stack corrodes, if the cryogenic storage develops a leak, then fuel production stops. And if fuel production stops for too long, you do not have enough fuel for the return trip. And if you do not have enough fuel, you are not going home. And there is another critical input that I have not mentioned yet. Hydrogen. The Sabatier process requires hydrogen as a feedstock. Where does the hydrogen come from? Water. Mars has water, frozen as ice beneath the surface and at the polar ice caps. But accessing it is not straightforward. Subsurface water ice deposits are buried under layers of regolith. Mining them requires drilling or excavation equipment. The ice must then be heated to melt it, and the water must be transported to the processing facility. All of this requires additional equipment, additional power, and additional operational complexity. And we are talking about mining enough water to produce enough hydrogen to manufacture over 1,000 metric tons of propellant. This is not a small operation. This is an industrial mining and processing operation on Mars run by a handful of astronauts who are also busy keeping themselves alive. Do you see the magnitude of this problem? The plan to return from Mars depends on establishing an entire industrial infrastructure on the surface of an alien planet. A chemical processing plant. A mining operation. A power generation facility. Cryogenic fuel storage. All of this must be set up, tested, and producing fuel before the crew arrives. The current plan calls for sending unmanned cargo missions to Mars years before the human mission, carrying the ISRO equipment and robots to set it all up. But this approach has never been tested. We have never sent industrial equipment to Mars. We have never operated an autonomous mining operation on another planet. We have never produced and stored cryogenic propellants on Mars. Every single step of this plan involves technologies and operations that have never been demonstrated at the required scale. And any failure at any step could mean the difference between coming home and dying on Mars. Now, even if we solve the fuel problem, even if we successfully manufacture over 1,000 metric tons of propellant on Mars, there is the issue of the launch itself. Launching a rocket from Mars is not like launching a rocket from Earth. On Earth, we have massive launch complexes with gantries, fueling systems, clean rooms, launch pads, lightning towers, tracking stations, and thousands of trained engineers and technicians who inspect, maintain, and operate everything. On Mars, you have none of that. The rocket has to survive sitting on the Martian surface for months, possibly over a year, while the fuel is being manufactured and loaded. During that time, it is exposed to temperature extremes that cycle from relatively warm during the day to brutally cold at night. It is exposed to dust that coats every surface and works its way into every joint and seal. It is exposed to radiation that can degrade materials and electronics. It is exposed to wind that, while not particularly strong in terms of force due to the thin atmosphere, carries abrasive dust particles that can erode surfaces over time. When launch day finally comes, the astronauts themselves must prepare and execute the launch. On Earth, a rocket launch is the culmination of months of preparation by thousands of specialists. On Mars, 4 to 6 people, who have spent over a year on an alien planet, who are physically weakened by radiation and reduced gravity, who are psychologically strained by isolation and confinement, must perform every task. They must check every system. They must fuel the rocket. They must seal themselves inside. They must run through the pre-launch checklist. They must ignite the engines and fly. And if something goes wrong during the launch, if an engine fails, if a fuel line leaks, if a navigation error occurs, there is no launch abort system that sends them safely back to the surface. There is no rescue team standing by. There is just the Martian wasteland below and the void of space above. Get it right or die. Suppose they do get off Mars. Suppose the ISRO worked perfectly, the launch was flawless, and the crew is now in Mars orbit, beginning their 7-month journey back to Earth. What happens now? Well, now they face the return transit, and it is in many ways worse than the outbound journey, because the astronauts are not the same people who left Earth 2.5 years ago. They are diminished versions of themselves. Their bones are thinner, their muscles are weaker, their hearts are deconditioned, their vision may be impaired, their DNA has accumulated months of radiation damage, their immune systems are suppressed, their cognitive function may be reduced, and now they are going back into microgravity. 7 more months of 0G, 7 more months of bone loss on top of bones that are already weakened, 7 more months of muscle atrophy on top of muscles that are already wasted, 7 more months of cardiovascular deconditioning on top of a heart that is already deconditioned, 7 more months of radiation exposure on top of a body that has already absorbed a lifetime's worth of radiation. The cumulative effect is devastating. By the time they reach Earth, after approximately 2.5 to 3 years of reduced gravity, radiation, confinement, and physical deterioration, they will be, physically speaking, shadows of their former selves. And then comes re-entry, entering Earth's atmosphere at speeds of around 28,000 kilometers per hour, decelerating through atmospheric friction, experiencing g-forces of approximately 3 to 4 times Earth's gravity. 3 to 4 g. That means their body weight effectively triples or quadruples for several minutes. A person who weighs 80 kilograms on Earth will feel as though they weigh 240 to 320 kilograms during re-entry. Now think about what this does to bones that have lost 15 to 25% of their mineral density. Think about what this does to a cardiovascular system that has been operating in reduced gravity for the better part of 3 years. Think about what this does to muscles that have atrophied significantly. The G-forces of re-entry, which are perfectly survivable for a healthy person in good physical condition, could be genuinely dangerous, potentially life-threatening, for someone whose body has been degraded by years of spaceflight. Compression fractures of the spine, cardiac arrhythmias or even cardiac arrest, loss of consciousness from insufficient blood flow to the brain. These are not theoretical risks. They are physiological certainties for a body that has been damaged enough, and even if the astronauts survive re-entry and land safely on Earth, their ordeal is not over. Readaptation to Earth gravity after extended time in reduced gravity is a brutal process. After just 6 months on the ISS, astronauts are often unable to walk unassisted when they return to Earth. They are carried from their capsules. They spend weeks in physical rehabilitation, and that is after 6 months in microgravity with extensive exercise countermeasures on a well-equipped space station. Mars return astronauts will have spent over 2 years in reduced gravity with fewer exercise options and greater physical degradation. The rehabilitation process could take months. Some effects might never fully reverse. Bone density lost over years may never be fully regained. Muscle mass lost over years may never fully recover. Vision changes from prolonged intracranial pressure may be permanent. Radiation damage to DNA is cumulative and irreversible. The person who returns from Mars, if they return at all, will not be the same person who left. They will be older, weaker, sicker, and permanently changed by an experience that pushed the human body far beyond what it was designed to endure. I want to pause here for a moment and talk about something that ties all of these physical challenges together in a way that most people do not appreciate. And that is the concept of the 26-month trap. Because of orbital mechanics, as we discussed, the return window from Mars only opens every 26 months. This means that everything must be ready at the exact right time, or you wait another 2+ years. The fuel must be produced and loaded, the rocket must be functional, the crew must be healthy enough to fly, the weather must cooperate, the communication link must be active. Every system must be go. If any single element is not ready, you miss the window. And missing the window is not just an inconvenience, it is a potentially fatal escalation. Every additional 26 months on Mars means 26 more months of radiation exposure, pushing closer to or beyond lifetime dose limits. It means 26 more months of bone and muscle deterioration. It means 26 more months of psychological stress. It means 26 more months of equipment wear and potential failure. It means 26 more months of food and water consumption, depleting supplies that were calculated for a specific mission duration. Each missed window makes the next return attempt harder. The crew is weaker. The equipment is older. The supplies are lower. The radiation damage is greater. It is a downward spiral, and if enough windows are missed, return becomes not just difficult, but genuinely impossible. The crew's physical condition deteriorates to the point where they cannot survive the return journey, or the equipment fails beyond the ability to repair, or the supplies run out. This is the 26-month trap, and it is one of the most insidious dangers of a Mars mission. Now, I know that many of you watching this are thinking about SpaceX, about Elon Musk, about Starship, about all the grand plans for Mars colonization that have been presented with such confident enthusiasm. And I want to address this directly, because I think it is important to separate the vision from the reality. Elon Musk's vision for Mars is genuinely inspiring. He envisions sending multiple starships to Mars, establishing a permanent base, eventually building a self-sustaining city of 1 million people. He talks about making humanity a multi-planetary species, about ensuring the long-term survival of our civilization by spreading beyond Earth. These are noble, exciting, and potentially species-saving goals. I am not here to mock or dismiss them. But I am here to be honest about where we actually are versus where we want to be. SpaceX's Starship is the most powerful rocket ever built. It is designed to be fully reusable. It can carry over 100 metric tons to low Earth orbit. It is a genuine engineering marvel. But as of now, Starship is still in the testing phase. It has not gone to Mars. It has not landed on Mars. It has not been refueled on Mars. It has not launched from Mars. None of the technologies required for the return trip, ISRU fuel production at scale, cryogenic storage on Mars, autonomous launch operations, have been demonstrated. Musk himself has been remarkably candid about the risks. He has said that going to Mars is not for the faint of heart. He has acknowledged that there is a good chance of death. He originally said humans would be on Mars by 2024, then by 2026, then by 2028. And the timeline continues to shift. This is not a criticism of Musk or SpaceX. The problem is genuinely hard, and timelines for genuinely hard problems always slip. But it is a reality check. The confident animations of starships landing on and launching from Mars are aspirational, not demonstrated. They represent where SpaceX hopes to be, not where SpaceX is. And the gap between hope and reality, when it comes to returning from Mars, is measured in decades of technological development, hundreds of billions of dollars, and the potential lives of the brave astronauts who go first. I want to tell you about something that happened in the early part of the last decade that I think perfectly illustrates the gap between the dream of Mars and the reality. In 2012, a Dutch entrepreneur named Bas Lansdorp founded a company called Mars One. The premise was audacious and simple. Mars One would send humans to Mars to establish the first permanent human settlement on another planet. The catch? It was explicitly a one-way trip. There was no plan for a return. The settlers would go to Mars and stay there for the rest of their lives. Mars One captured the world's imagination. Over 200,000 people from countries around the globe applied to be among the first settlers. 200,000 people who were willing to leave Earth forever. They were scientists, engineers, teachers, students, adventurers, dreamers. They went through selection rounds. They appeared on television. They became minor celebrities. The world watched, fascinated, as ordinary people volunteered for what was essentially a slow-motion act of willing exile. But as the initial excitement faded, the cracks began to show. In 2014, researchers at the Massachusetts Institute of Technology conducted a detailed analysis of Mars One's mission plans. Their findings were devastating. The MIT team concluded that settlers would begin dying within 68 days of landing. The habitat design was flawed. The oxygen management system would produce toxic levels of oxygen from the plants used for food production. The technology required for many critical systems simply did not exist. The budget, which was supposed to come primarily from selling television rights to a reality show about the settlers, was a tiny fraction of what a Mars mission would actually cost. Even the most optimistic estimates for a basic Mars mission run into tens of billions of dollars. Mars One's total funding was measured in millions, not even tens of millions. Single-digit millions. Former NASA scientists and engineers reviewed the Mars One plans and used words like delusional and technically impossible. The mission was never going to work. It was never even close to working. And in January 2019, Mars One Ventures was declared bankrupt, with less than $25,000 in its bank accounts and approximately 1.1 million euros in debt. Less than $25,000. You probably have more money in your checking account than Mars One had when it went under. The 200,000 people who applied to die on Mars were left with nothing. No mission. No refund for whatever they had invested in the dream. No answers about how a company that promised them passage to another world could not even keep its own lights on. Mars One was widely criticized as either an elaborate scam or an exercise in delusional optimism, and the truth probably contains elements of both. But I think the most important lesson of Mars One is not about the failure of the company. It is about the people who volunteered. 200,000 people were willing to leave Earth forever, to go to Mars knowing they would never come back, based on a plan so flawed that it would have killed them in 68 days. This tells us something profound about human nature. It tells us that the desire to explore, the pull of the unknown, the dream of being the first to stand on an alien world is so powerful that it overrides even the survival instinct. People will volunteer for near-certain death if you wrap it in enough adventure and purpose. And this raises ethical questions that we as a society have not yet answered. Should we allow people to volunteer for missions with extremely high mortality risk? At what point does informed consent stop being meaningful? When someone says, "I volunteer to die on Mars," is that a courageous, autonomous decision that we should respect? Or is it a symptom of something else? Desperation, delusion, a desire for escape? These are not easy questions, and they will become urgent ones when the first real Mars missions begin accepting crew. I have been painting a picture of Mars that is, admittedly, quite grim, and everything I have told you is scientifically accurate, based on data from NASA, ESA, peer-reviewed research, and the first-hand observations of instruments and rovers that are right now sitting on the Martian surface. But I would be doing you a disservice if I did not also tell you about Mars's backstory. Because Mars was not always the dead, frozen, irradiated wasteland it is today. 4 billion years ago, Mars was a different world. A world that, if you could travel back in time and stand on its surface, you might mistake for a young Earth. And understanding what Mars used to be and how it became what it is today is crucial to understanding both the dangers and the allure of the red planet. 4 billion years ago, Mars had a thick atmosphere, not as thick as Earth's today, but thick enough to maintain surface pressure that allowed liquid water to exist. And Mars had liquid water, not just a little bit. Oceans of it. Rivers carved channels across the Martian surface that are still visible today from orbit. Lake beds filled with sediment that Curiosity and Perseverance have rolled across and examined up close. Mineral deposits, like hematite and clay minerals, that can only form in the presence of liquid water over extended periods. The evidence is overwhelming. Early Mars was a warm, wet world with a substantial atmosphere and flowing water. It had, as far as we can tell, all the basic ingredients for life, water, warmth, organic chemistry, and energy from the sun. Whether life actually arose on Mars during this period is one of the most tantalizing open questions in science. We do not know yet, but the conditions were there. If life could arise on early Earth, there is no obvious reason it could not have arisen on early Mars as well. So what happened? How did Mars go from a potentially habitable watery world to the frozen desert we see today? The answer lies deep inside the planet, in its core. Mars is smaller than Earth, about half the diameter, with about 1/10 the mass. This means Mars's interior contains less radioactive material, less residual heat from its formation, and a smaller metallic core. And that smaller core cooled faster. On Earth, the outer core is still molten, a churning sea of liquid iron and nickel that generates our planet's magnetic field through a process called the dynamo. This magnetic field extends thousands of kilometers into space, creating the magnetosphere that deflects solar wind and cosmic radiation. It is, without exaggeration, one of the primary reasons life exists on Earth. Mars had a similar magnetic field early in its history, generated by its own molten core. But because Mars is smaller, its core cooled faster. Approximately 4 billion years ago, give or take, Mars's core solidified enough that the dynamo effect weakened and eventually stopped. The magnetic field collapsed. And this was the beginning of the end for Mars as a habitable world. Without a magnetic field, Mars was exposed directly to the solar wind, that constant stream of charged particles emanating from the sun. The solar wind began to interact directly with Mars's upper atmosphere, stripping away gas molecules through a process called sputtering. Ultraviolet radiation from the sun, which the magnetic field had previously helped deflect, began to break apart atmospheric molecules, making them light enough to escape Mars's weaker gravity. Over hundreds of millions of years, the atmosphere was eroded, molecule by molecule, blown away into space by the relentless pressure of the solar wind. NASA's MAVEN mission, which arrived at Mars in 2014, confirmed this process directly. MAVEN measured the rate at which Mars is still losing atmosphere today, approximately 100 grams per second. That does not sound like much, but over 4 billion years, it adds up to a catastrophic loss. As the atmosphere thinned, several devastating consequences followed in a chain reaction. Surface pressure dropped. The lower pressure meant that liquid water could no longer exist on the surface. Water either froze, soaking into the ground as permafrost, or evaporated and was lost to space. The greenhouse effect weakened as the atmosphere thinned, causing temperatures to plummet. UV radiation began reaching the surface in lethal quantities, sterilizing the ground. The water cycle stopped. The weather patterns that had moved water and heat around the planet ceased. Mars dried out. It froze. It died. Or, at least, it became what we see today. A cold, dry, irradiated world with a paper-thin atmosphere, no liquid water on the surface, and soil laced with toxic chemicals that would have been washed away by rain if rain still fell. This story, the story of how Mars died, is not just ancient history, it is directly relevant to our topic. because it is the reason Mars is so hostile to human life today. Every single danger we have discussed, the thin atmosphere, the lack of oxygen, the extreme cold, the surface radiation, the absence of liquid water, the toxic perchlorates in the soil, all of these are consequences of Mars losing its magnetic field 4 billion years ago. A single geological event, the cooling of a planetary core, set off a chain reaction that turned a potentially habitable world into a death trap. And it happened slowly, over millions of years. Mars did not die suddenly. It died gradually, imperceptibly, one atmospheric molecule at a time. There is a lesson in this for Earth as well. Our magnetic field, our atmosphere, our water, our moderate temperatures, we take these things for granted. But Mars shows us that they are not guaranteed. They depend on the internal processes of our planet, on the molten churning of our core, on the thickness of our atmospheric blanket. If those processes were to change, if Earth's magnetic field were to weaken significantly, our planet could follow Mars's trajectory. Not quickly, not in our lifetimes, but over geological time. Mars is not just a destination for exploration, it is a cautionary tale about planetary fragility. Some people have proposed terraforming Mars, the idea of deliberately altering the planet's climate and atmosphere to make it more Earth-like. The concepts are varied and creative. Release CO2 from the polar ice caps and soil to thicken the atmosphere. Redirect comets to crash into Mars, delivering water and volatiles. Place a giant magnetic shield at the L1 Lagrange point between Mars and the Sun, artificially recreating a magnetic field that would protect the atmosphere from solar wind erosion. These ideas are fascinating thought experiments, but the scientific consensus is sobering. Studies have shown that Mars simply does not have enough accessible CO2 reserves to create an atmosphere thick enough to support human life, even if we could release all of it. The water ice on Mars, while substantial, is not enough to create oceans, and the magnetic shield concept, while physically plausible, would require engineering on a scale beyond anything we have ever attempted. Terraforming Mars is a project measured in centuries or millennia, not decades. It is not going to help the first astronauts who land there. They will face Mars as it is, a dead world with a poisoned surface and a vanishing atmosphere, and they will have to survive it with whatever technology they bring with them. Let me shift gears now and talk about something that might seem less dramatic than radiation or toxic soil, but is just as fundamental to the question of survival and return. Food and water, because human beings need to eat and drink to survive, and on Mars, both of these basic needs become extraordinarily complex challenges. A Mars mission for 6 people lasting approximately 2.5 to 3 years requires roughly 10 to 12,000 kilograms of food if everything is brought from Earth. That is 10 to 12 metric tons of food, and there is a problem with bringing that much food from Earth beyond just the weight. Food has a shelf life. Space food, specially processed and packaged for long-duration missions, can last 2 to 3 years before it begins to lose nutritional value. Vitamins degrade. Fats go rancid. Textures change. Flavors fade. By the time astronauts on Mars are eating food that was packed before they left Earth, it could be 2 to 3 years old, and its nutritional content could be significantly diminished. Over a long mission, this could lead to nutritional deficiencies that compound the health problems already caused by radiation, microgravity, and stress. The alternative, or more likely the supplement to prepackaged food, is growing food on Mars. And this is where things get complicated. Mars has soil, yes, but as we discussed, it is toxic. Before you can grow anything in Martian regolith, you have to remove the perchlorates and other toxic compounds. This is doable but adds complexity and requires water, energy, and processing equipment. The more practical approach is hydroponics, growing plants in nutrient-rich water without soil. Hydroponic systems are more efficient than soil-based agriculture, and they avoid the perchlorate problem entirely. But they come with their own challenges. Hydroponic systems require a sealed, pressurized, temperature-controlled, and illuminated environment. a greenhouse on Mars. Mars receives only about 43% as much sunlight as Earth, so even a greenhouse with transparent walls might not provide enough light for robust plant growth. Supplemental artificial lighting would be needed, which requires electrical power. And power, as we discussed, is a precious and potentially unreliable resource on Mars, especially during dust storms. There is also the problem of biological contamination. Hydroponic systems are warm, moist environments, which are ideal for not just plants but also bacteria and fungi. On Earth, if a greenhouse gets a fungal infection, you can treat it or start over with readily available supplies. On Mars, a fungal infection in the hydroponic system could devastate the food supply, and the antifungal treatments available would be limited to whatever was brought from Earth. There are no garden centers on Mars. Water is perhaps the single most critical resource for a Mars mission. It is needed for drinking, cooking, hygiene, medical use, plant watering, oxygen production through electrolysis, and, as we discussed, fuel production. Mars has water frozen as ice beneath the surface, especially at higher latitudes. But accessing this water is a major challenge. The ice is buried under layers of regolith, sometimes just a few centimeters down, sometimes meters deep. Mining it requires drilling or excavation equipment that must operate in the extreme cold and dust of the Martian surface. Once mined, the ice must be heated to melt it, then purified, then distributed to wherever it is needed. All of this requires energy and infrastructure, and every system in this chain must be reliable, because water cannot be improvised. If the water extraction system fails and cannot be repaired, the crew faces dehydration and death within days. The International Space Station has demonstrated that water recycling can recover about 90% of wastewater, including from urine and humidity in the air. A Mars habitat would use similar systems, but even with 90% recovery, there are losses that must be replenished from external sources. And a failure in the water recycling system, a common occurrence on the ISS that requires regular maintenance and spare parts, would be far more serious on Mars, where spare parts are limited to whatever was brought along. Energy ties everything together. Every system that keeps astronauts alive on Mars requires power. Life support, heating, water extraction, food production, communications, ISRU fuel production, lighting, computers, medical equipment, everything runs on electricity. A power failure on Mars is not like a power failure on Earth, where you light some candles and wait for the utility company to fix the problem. On Mars, a prolonged power failure means the heating system stops. The temperature inside the habitat begins to drop toward the -60°C external temperature. The CO2 scrubbers stop working, carbon dioxide builds up in the air, the water recycling system stops, the food production lights go out. Within hours, the situation becomes critical. Within days, without power, the crew is dead. This is why power system redundancy is absolutely essential for a Mars mission, and why many mission designers are now advocating for nuclear power as the primary energy source. Nuclear systems, whether small fission reactors or radioisotope thermoelectric generators, provide steady, reliable power regardless of dust storms, regardless of day-night cycles, regardless of Mars's distance from the Sun. But nuclear power systems for Mars surface operations are still in development. They are heavy, expensive, require careful shielding to protect the crew from the reactor's own radiation, and have never been tested in the Martian environment. Solar panels are lighter and simpler, but are vulnerable to dust storms and limited by the reduced solar intensity at Mars's distance from the Sun. The ideal solution is probably a combination of both, solar panels supplemented by nuclear backup. But this adds complexity, mass and cost to an already overwhelmingly complex, massive and costly mission. I want to bring us now to the psychology of long-duration Mars habitation, because I think this is one of the most underappreciated threats to mission success and crew survival. We have talked about the psychological challenges of the 7-month transit, but the transit is temporary. It has a defined endpoint. You are going somewhere, and you will arrive. Once on Mars, the psychological challenges shift and in many ways intensify, because now you are not going somewhere. You are there. And there is a specific place that happens to be the most isolated, hostile, an alien environment any human being has ever lived in. The first psychological challenge is the environment itself. Mars is beautiful in an austere, desolate way. Rusty red landscapes stretching to the horizon, ancient craters and valleys carved by water that disappeared billions of years ago, a sky that shifts from butterscotch during the day to deep blue at twilight. But it is also lifeless. Utterly, completely, absolutely lifeless. There are no trees, no grass, no flowers, no insects, no birds, no animals, no sound of wind rustling through leaves, no smell of rain, no taste of fresh food pulled from a garden. Nothing alive except the crew themselves and whatever plants they manage to grow in their hydroponic systems. Humans are social biological creatures. We evolved surrounded by life, by the sounds, smells, sights and sensations of a living world. Being permanently embedded in a dead landscape where nothing moves except dust, where nothing grows except what you plant, where nothing makes a sound except the hum of your life support machinery, is psychologically corrosive in ways that are difficult to predict and impossible to fully prepare for. Some researchers have compared it to a mild form of sensory deprivation, which is known to cause hallucinations, paranoia, and cognitive decline over extended periods. The second challenge is communication with Earth. We have discussed the time delay, 4 to 24 minutes each way. What this means in practice is that real-time conversation is impossible. You cannot call your family and have a normal conversation. You cannot video chat with your children. You cannot have a back-and-forth discussion with your spouse or your friends. You can send messages, video recordings, emails, and then wait anywhere from 8 to 48 minutes for a response. This asynchronous communication, while better than nothing, does not fulfill the deep human need for real-time social connection. It is like communicating entirely through letters, except the letters take 20 minutes to arrive instead of days. Over time, this communication lag erodes the sense of connection with people on Earth. Relationships strain under the weight of distance and delay. Marriages have ended during much shorter and less isolated deployments. Friendships fade. The crew on Mars increasingly exists in their own world, psychologically as well as physically separated from Earth. And the longer the mission continues, the wider this psychological gulf becomes. The third challenge, and perhaps the most insidious, is what psychologists call the meaning crisis. In the first weeks and months on Mars, everything is new. Every rock is a discovery. Every sunset is a spectacle. Every day brings novel challenges and experiences. The crew is energized by the historic significance of what they are doing. They are the first humans on another planet. That is extraordinary. But human psychology is remarkably adaptable, and what is extraordinary today becomes routine tomorrow. The Martian landscape, however beautiful, is the same landscape every day. The same rusty plains, the same cold, dusty air seen through habitat windows, the same processed food, the same exercise routine, the same faces, the same conversations, the same cramped habitat. The excitement of discovery gives way to the monotony of survival, and when the novelty wears off, the crew is left with a stark question. Why am I here? What is the point of all this suffering? The scientific mission provides some answer, but science is methodical, slow, and often tedious. It does not always provide the kind of immediate, visceral purpose that sustains psychological well-being. The crew must find meaning and motivation to continue functioning at a high level day after day, month after month, for over a year, in an environment that is actively hostile to their physical and psychological health, with the knowledge that they might not survive the return trip. Finding and maintaining that meaning is one of the greatest psychological challenges of a Mars mission. and it is one for which there is no clear solution. Let me now talk about the medical challenges on Mars, because they tie together many of the threats we have discussed and add new ones of their own. On Earth, if you have a medical emergency, you call an ambulance. Paramedics arrive in minutes. You are taken to a hospital with specialized equipment, trained doctors, pharmacies full of medications, and the full support of modern medical infrastructure. On the ISS, if an astronaut has a medical emergency, they can be evacuated to Earth within hours using the always docked crew vehicle. Doctors on Earth can provide real-time guidance by radio. On Mars, none of this is available. There is no ambulance. There is no hospital. There is no evacuation. There is no real-time communication with doctors. If a crew member has a medical emergency on Mars, the other crew members must diagnose and treat the condition themselves, using whatever medical equipment and supplies they brought with them, guided only by their training and whatever delayed consultation they can get from Earth. Consider the kinds of medical emergencies that could occur. Acute appendicitis, a common condition that affects about 7% of people at some point in their lives. On Earth, it is treated with surgery, a routine procedure in any hospital. On Mars, one of the crew members, who has received some surgical training but is not a professional surgeon, must perform an appendectomy using basic surgical instruments in a makeshift operating theatre, while the patient is under whatever sedation is available. If the appendix ruptures before surgery can be performed, peritonitis sets in, a life-threatening infection of the abdominal cavity that requires intravenous antibiotics and possibly further surgery. The chances of a successful outcome on Mars are significantly lower than on Earth. Kidney stones, which we mentioned earlier as a risk factor due to bone density loss releasing calcium into the bloodstream, cause excruciating pain and, if they block the urinary tract, can lead to kidney damage and sepsis. On Earth, small kidney stones pass on their own with pain management, and larger ones are treated with lithotripsy or surgical removal. On Mars, lithotripsy equipment is unlikely to be available due to its size and weight. Surgical intervention would carry the same risks as the appendectomy scenario. Dental emergencies, tooth fractures, abscesses, severe cavities are common enough that at least one would be statistically likely during a multi-year mission. A dental abscess, if untreated, can lead to a life-threatening blood infection. The crew would need basic dental capabilities, but full dental care is beyond what can be reasonably packed for a Mars mission. Traumatic injuries from accidents during EVAs or habitat maintenance, broken bones, lacerations, head injuries would need to be treated on site with limited resources. And psychological emergencies, severe depression, psychotic episodes, anxiety attacks would need to be managed by crew members who are themselves under extreme stress and may have limited psychiatric training. There is also the longer-term medical concern of radiation-induced illness. As we discussed, the cumulative radiation dose on a Mars mission could exceed 1 sievert. At this level, some crew members might begin to develop early signs of radiation injury during the mission itself, not just after returning to Earth. Fatigue, immunosuppression, cognitive changes, increased susceptibility to infections. These symptoms would be difficult to distinguish from the effects of stress and isolation, which means they might go unrecognized until they become serious. And the medications available to treat radiation-related conditions are limited. There is no radiation therapy on Mars. There is no oncology ward. If a crew member develops cancer during the mission, there is nothing to do but manage symptoms and hope for the best. I want to bring together all of these threads now, because I think when you see them all at once, the full picture becomes clear. Let us walk through the entire Mars mission from start to finish and see how the challenges compound. You launch from Earth. From the moment you clear the atmosphere, you are in the radiation bath of deep space. Cosmic rays are breaking your DNA. Solar flares threaten lethal doses. You are in microgravity. Your bones begin to dissolve. Your muscles begin to atrophy. Your heart begins to weaken. Your eyes begin to change. Your immune system begins to falter. Psychologically, you are watching Earth shrink to a point of light. You cannot have real-time conversations with anyone you love. You are confined in a small space with the same people for 7 months, with no escape. Somewhere around month 5, the third quarter phenomenon hits, and morale drops. But you push through, because Mars is ahead. You arrive at Mars. You attempt the most dangerous landing in the history of spaceflight, in a vehicle heavier than anything ever landed on Mars, using technology that has never been tested at this scale, completely autonomously because the communication delay makes Earth useless during idle. Your weakened body endures several Gs of deceleration. You land. You step onto the surface. You are the first human being on another planet. The whole world celebrates. And then reality sets in. The atmosphere will kill you in seconds without a suit. The soil is toxic. The radiation is 67 times Earth's level. The temperature can drop to negative 150 degrees. Dust storms can engulf the planet for months. Your gravity is 38% of what you evolved in. You cannot go outside without extensive preparation and protective equipment. Your habitat is small, your resources are limited, and your nearest help is 225 million kilometers away. You begin the work of surviving, maintaining life support, producing water, growing food, generating power, monitoring radiation levels, conducting science, checking and maintaining equipment, exercising to combat the physical deterioration that may or may not be slowed by Mars gravity. And all the while, in the background, the Israfil production system is supposedly churning out propellant for your return trip. Day after day, month after month, for over 500 days. The novelty of Mars fades. The landscape becomes routine. The same red dust, the same thin sky, the same processed food, the same small habitat, the same faces. You miss Earth with an ache that goes beyond homesickness. You miss rain, you miss wind in your hair, you miss the smell of grass, you miss the sound of birds, you miss the weight of your own body in full gravity. You miss being able to walk outside without a suit. You miss the feeling of being part of a living world, not a dead one. The return window approaches. The fuel production is checked. Is there enough? Are all the systems functional? Is the launch vehicle intact after over a year on the Martian surface? Is the crew healthy enough to fly? Maybe everything checks out. Maybe the mission goes perfectly, and you launch from Mars, endure another 7 months of radiation and microgravity, and somehow survive re-entry into Earth's atmosphere with your weakened body. Maybe, but maybe the fuel production fell short because a compressor failed during a dust storm and could not be repaired in time. Maybe one of the propellant tanks developed a leak from thermal cycling. Maybe a crew member has a medical condition that makes the G-forces of launch and re-entry too risky. Maybe a global dust storm hits right when you need to launch, making surface operations impossible. Maybe an unforeseen engineering problem makes the launch vehicle unsafe to fly. In any of these scenarios, you miss the window. And you wait another 26 months, and the clock of deterioration ticks on. More radiation, more physical decline, more psychological strain, more equipment wear, less food, less water, less of everything except danger. This is why the title of this video is not hyperbole. It is not clickbait. It is a sober scientific assessment of the cumulative reality of a Mars mission. Anyone who steps foot on Mars faces a genuine, scientifically supported probability that they will never return to Earth. Not because they choose to stay, but because the physics, the biology, the engineering, and the logistics conspire to make the return trip one of the most difficult challenges human beings have ever attempted, with a failure rate that honest scientists and engineers acknowledge could be very high. But I do not want to end this discussion on a note of pure pessimism, because that would be dishonest too. The truth is more nuanced than either the utopian visions of easy Mars colonization or the fatalistic view that Mars is forever beyond our reach. The truth is that we are making progress. Real, measurable, significant progress towards solving the challenges of Mars exploration and return. And I want to talk about that progress, because it is part of the story too, and you deserve to hear it. Let us start with radiation protection. This is one of the most challenging problems, but there are several promising approaches being developed. Hydrogenated boron nitride nanotubes, or BNNTs, are a material that combines excellent structural properties with effective radiation shielding. The hydrogen atoms in BNNTs are particularly good at absorbing neutrons, and the boron is excellent at capturing secondary radiation. These nanotubes are flexible enough to be woven into fabric, which means they could potentially be incorporated into spacesuits, habitat walls, and vehicle structures. They are still in development, but the early results are encouraging. Underground habitats offer another approach. Mars has lava tubes, tunnels carved by flowing lava billions of years ago when Mars was volcanically active. Some of these lava tubes are enormous, potentially hundreds of meters in diameter. If a habitat could be established inside a lava tube, the rock above would provide excellent radiation shielding, as well as insulation against temperature extremes. Locating, accessing, and establishing a habitat in a Martian lava tube would be extremely challenging, but it could solve or greatly reduce several of the most serious threats simultaneously.